I know. Oh, I can't tell you right now how long the next exam is going to be. Um, yeah, I'll know a little bit more later. I can't tell you right now how many problems, but we'll talk about it for sure before. Okay, so 4.1, we were talking about maximum and minimum values of a function on a closed interval. There's a major idea in this class, major result. So were there any questions on the homework finding critical numbers? Pretty straightforward. I tried to make sure that all the functions were nice functions. But now let's get into something, some of these functions are a little more complicated. So let's try some things I avoided on purpose. So how about something like, so no one had any issues with like number 31, right? What's that? Yeah. So anyone have a request for me to do any of the problems? No? Let me see. I asked you to do 23 through 25 or 35 odds. How about 33? Anybody do 33? Did y'all do your homework? I'm starting to get a sense that maybe there are no questions because you didn't get a chance to look at all of the homework. Or you understood it, which would be great. Let's try with this. Let's try, you're given f of theta is equal to 2 cosine theta plus sine squared theta. And all you're asked to do is find the critical numbers of this function. So that means you want to find where the function's derivative is 0 and where it's possibly undefined. And that's it. Okay? So take the derivative, set it to 0. Take the derivative, look to see if it's undefined anywhere. So you have to be able to compute the derivative, which in this case, f prime theta would be negative 2 sine theta, because derivative cosine is a negative sine, right? And then separate terms, so what's the derivative of sine squared? 2 comes out, this is chain rule, 2 sine theta, then the derivative of what's here, the derivative of sine theta is cosine theta. So there's your derivative. And you want to set that equal to 0. So let me set f prime equal to 0. So I take negative 2 sine theta plus 2 sine theta cosine theta equal to 0. And how would you solve that? You could do negative 2 sine out. And what would you be left with in there? You'd have a 1 here first, right? And then minus cosine theta. There we go. It all depends on what you pulled out of there. It was suggested that I pull a negative 2 sine out, so that's why I changed the signs of what was there. And then the whole reason we do that is because now you have multiplication. Negative 2 sine theta times 1 minus cosine theta. You set each of those factors equal to 0. So I take negative 2 sine theta, set it equal to 0. I set the other factor, 1 minus cosine theta, equal to 0. If you're coming in a little bit late, your related rates things are here. If you want to see if that one is yours or not. It says name on top. That's you? Can you put your name on and turn back in? All right. You probably had your name on the first page. Did you turn in the problems with it? I don't know. If anyone who turned in the problems with it, I tore that page off first because it just gets in my way when I'm grading. So, yeah, if it wasn't, yeah, no, most of the time it wasn't tearing. It was just moving it because it wasn't stapled. But okay, now look, this is pre-cal. Okay, this is pre-cal at this point. You're trying to find the solutions to this equation. In this equation, they're both trigonometric equations. So let me look at this first one. Negative 2 sine theta equals 0. I'll divide both sides by -2. That'll get rid of that. I get sine theta is 0. I'll take it right here. Negative sine theta, or no, sine theta is 0 still, right? And now you have to remember how to find the solutions of this. So what's the solution to that? When is sine of an angle 0? So I always go off the unit circle because I think it's the best way to look at trig functions. When you say sine of an angle, you're talking about the y-coordinate on the unit circle. And you're saying, where's the y-coordinate on the unit circle 0? That happens here, and that happens here. So I was hearing 0 and 2 pi. Everyone agrees 0 and 2 pi, not 2 pi. 0 and pi are two answers? Are they the only two answers? That's the issue we have to deal with here. You could have 0, you could have pi, you could have 2 pi, you could have 3 pi, you could have 4 pi, you could have 5 pi. You could have also gone backwards and had negative pi, negative 2 pi, negative 3 pi. So in a pre-cal class, you find what's called the general solution. The general solution would be all the angles that would create those 2 points. And what I'm realizing by looking at this is that if I started at an angle of 0, then if I add pi, I'm here. I add another pi, I'm back to this one. Add another pi, I'm here. And I could have gone counterclockwise by adding negative pi, then negative 2 pi. So it looks like if I let my angle, theta, be equal to 0 plus any multiple of pi, so the way I write that is pi k, where k here is understood to be an integer. So k can be 0, k can be 1, 2, 3, 4, 5 forever, or it can be -1, -2, -3, -4. And if you look at that, that gives you all possible answers, all infinitely many answers. So yeah, that's the next time I say, do we really need the 0? No, you don't. So you can just put pi k. So theta is pi k. Now some books will not use k. Some books will use n. Just be prepared for that as you move forward and do more math. Here I'm saying k is an integer. Have we talked about the symbol for integers? Double struck z? Have I shown you all that? No, I haven't shown you all that. Double struck r is the real numbers, right? Yes? Double struck z, double struck is the, drawing this line twice, double struck. A double struck capital Z is the integers. Double struck C is the complex numbers. There's a bunch of them. I mean, we don't need to get into that. Double struck N is the natural numbers. Just go look it up on Google or something. So I'm saying K is an element of the integers here. You don't have to write that on your answers as long as we all understand and agree what we mean by K. K can't be a fraction though, okay? K can't be 1/2. Because if you plug in 1/2, half of pi, pi over 2, sine's not 0. Okay, so far that's where I am, right? Now go look at the other equation. And I'm going to move things around here. This is cosine theta is 1, right? Where is cosine theta 1? Well, luckily for me, it's the same thing, right? Cosine, now I'm looking at the x-coordinate, saying when is the x-coordinate 1? It only happens at that value right there, which is actually 0. All the way around would be 2 pi, right? Or 4 pi, or 6 pi, or backwards. But this covers that, doesn't it? This covers it. So what I recommend you should do when you're doing these problems is draw all your answers on one circle and see if you've got them covered. So I had the 2 here, and then I had that other one there, and they overlapped, right? This answer should take care of all of them. With me? We're done? What have I not checked? This was just the derivative being 0, right? I need to also check when the derivative is undefined. So is the derivative undefined? Question. Well, the derivative was -2 sine theta plus 2 sine theta cosine theta, right? That was the derivative. And my question here is there a theta that I can plug in that's within the domain of the function, the original function, before I took the derivative, and that'll cause that to be undefined? No, because sine is always undefined, right? Cosine's always undefined. You're just adding and multiplying them. That should be well behaved. So is this ever undefined? No. Therefore, you don't have any other critical numbers. But you have an infinite number of them, don't you? All the multiples of pi? Okay. Now I'll ask again since more of you showed up. Any requests on the homework? Any problems that you'd like me to do? No? 31? Yeah. Didn't I asked if anyone, right? Because I had a feeling 31 might cause problems. 31. All right. So 31 was capital F of x equals x to the 4/5 times, in parentheses, x minus 4 squared. I'm finding the critical number, so all I'm doing is I'm trying to figure out where the derivative is 0 and undefined, if possible. So first, my derivative, capital F prime of x, is going to be some product rule, because I have a product between these two factors, and then this one is going to be a little chain rule, isn't it? All right, so product rule says I take the derivative of this first one, which is a power rule. So derivative of the first one is 4/5 x to the -1/5. Now times the second function without any derivative taken, then plus the derivative of this second function, which is what? 2 parentheses x minus 4, then times 1, which you can write or not write, and then times x to the 4/5, finishing off the product rule. Any questions on that? By the way, again, if you came in a little late, the related rate problems are right here. I graded them. You can pick them up if you turn them in. And I counted those for 2 quiz grades. Just so you know, if you're looking at your grades, the last 2 quizzes are off of that assignment. What bonus? Did I hand those back? Let me see. I may not have graded them yet. Have not graded them. I had a lot of other stuff that I wanted to get done with grades, so. All right, so now this is where we actually have to do something with this now, right? I mean, we can't just leave it like that and say when is that equal to 0. So you have to be able to clean this up. I always like to, you know, if I have negative exponents, drop them down, combine things together. All right, so this will become, how about 4x minus 4 squared over 5x to the 1/5, and then plus over here 2x minus 4 times x to the 4/5. All I did was drop this negative exponent down, and then it joined the 5 that was already down there. Other than that, I didn't really do a whole lot. And I'm going to want to set this equal to 0, right? So something that you might notice after you do enough of these is that when you have these weird fractions like this, when we wind up setting them equal to 0, sometimes, a lot of times, it's nice to be able to just get a common denominator between these and put them together. Like right now, this one doesn't have a denominator, but imagine that it's a 1, right? What could I use as my common denominator? 5x to the 1/5. Now, you may be saying, no, I do not want to make that a 5x to the 1/5 because I don't want to have to put that up here. But it's going to be nice what happens, all right? I'm going to multiply the top and bottom here by 5x to the 1/5 to create my common denominator. Now, I know I'm going to get a common denominator from that, so all of this is going to be over my common denominator. The top left fraction here does not change. And how does this top right one change? When I multiply, let's say, the 5 times the 2 out here, I get a 10. But what's x to the 4/5 times x to the 1/5? Just x, because you add the exponents. 4/5 plus 1/5 is 5/5. 5/5 is 1. So this is really going to turn into a plus 10x times x minus 4. Y'all see that? Isn't that nice? This right here times the 2 is this. Questions? All right, now I'm going to try and take this and see when this is 0. So the question is, when is that derivative equal to 0? So take that ugly thing and set it equal to 0. Now, this is a good opportunity to point something out, little side note, and this will come into play throughout your entire life as a math person. And I may have mentioned this already. If I did, sorry. The only way a fraction can be 0 is if what? The only way that that fraction can be 0 is what? The a has to be 0. It's the only way it can happen. Because you can always multiply both sides of this by b, can't you? And b over b here cancels, and over here 0 times anything is 0. So the next step of this line, the next part of this equation would be what? A equals 0, right? So you can always, from a divided by b equals 0, you always draw the conclusion that a must be 0. So the value of that is that if you have a, which is all this crap up here, over b equals 0, the only thing you really have to look at is what? The a. But you could not have done that back here before I got a common denominator because you did not have a over an entire b, right? It was two separate fractions, so you could not have used that rule. So that's why I always like to try and put the fractions together so I can use this rule. So this turns into 4 times x minus 4 squared plus 10x times x minus 4. That must be 0. And I have intentionally not multiplied this stuff out. Do you see why I have not multiplied it out? Yeah, I have a common factor, right? These both contain an x minus 4. And there's even a number in both of these, right? There's a 2 that goes into both of these. So I could, if I so wish to do so, pull a 2x minus 4 out of the entire thing. So what would be missing here? I pulled a 2 out of this 4, so I should still have a 2. And there was an x minus 4 squared. I pulled one of them, so I should be left with what? A single x minus 4? And then what about the next one? A 5? X. Good. because that 10 got reduced by 2, so I have 5, and then the x is there, and then this x minus 4 came out, so there we go. And then look inside this bracket, distribute your 2 through, and you're going to have just a nice linear expression in there. You have 2x minus 4 out here. This becomes what? 2x minus 8 plus 5x, which is 7x minus 8 equals 0. And now you have 1, 2, 3 things that multiply to be 0. So you set each one of them equal to 0, although you don't have to consider the 2, right? Because the 2 can never be 0. X minus 4 can be 0 only when x is 4. And then this one right here, setting that to 0, you get x equals 8/7. So I have 2 critical numbers. Any questions? 2 critical numbers so far? My denominator, remember I said this? Yep, I said, look, this is like a big A over a B equals 0, so all I have to really look at is the A. For now, though, because I do have to come back and look at one thing, and that's the next part of this. Remember, we have to look at when the derivative is undefined? Okay. But any questions on that? Okay, so now I'm going to go on to the next part. When is the derivative undefined? Is it? I don't even know. So go back up and look at your derivative. And when I say go back and look at it, I suggest you look at the actual derivative, like either this form or when we got a common denominator. I think the common denominator one really shows off where we have the problem. You see where we have a problem here? If x is 0, right? 0 to any power should be 0. And so we should get 5 times 0 is 0. I should get division by 0. But go back to the original function. Could you plug 0 in here? 0 to any power 0, 0 minus 4 squared. 0 is okay to plug in here, right? You can plug 0 into the original function, but you cannot plug 0 into the derivative. So 0 is a place where the derivative is undefined. Y'all follow that? It's very important because if the original function wasn't defined at 0, then we wouldn't care that 0 is a problem right now because 0 wasn't even allowed to begin with. But 0 is allowed into the original function, so we have to consider it. So my conclusion here is yes, at x equals 0. So that's my third critical number. All right? I'm going to have the computer do a quick graph, although I have had problems in the past with WinPlot being able to handle the graphs of these things. So let's see. It was x to the 4/5, right, times x minus 4 squared. I'm just going to see what this thing does. That's what I thought it would do. Undefined? Where it's, oh, it could happen, yes. Yeah, a rational function would be an example. Because anywhere you'd have an asymptote, you'd have an undefined. How would you find another one? You would, okay, so what are the things I'm looking for? I'm looking for things that cause a function to not work. So like division by zeros where I'd have a problem. And since this is the only place I'm dividing, I just ask myself, when is this 0? So I just set this to 0, which I hope that was like kind of an obvious answer. But let's say it was more complicated down here. You would take the entire thing and set it to 0. So maybe if everything down here was quadratic, you would set it to 0, and now you'd have to solve a quadratic equation. That makes sense? Okay, what else are things that are undefined? Square roots can't have negatives under square roots, so you'd have to look at that. Some trig functions aren't defined in certain places, right? Like tangent's not defined at pi over 2 and negative pi over 2, or so there are certain functions we would not be able to, that we would have to investigate. Okay, so the graph here, yeah, it's having some issues. Specifically, let's see. This is what this graph looks like, but you can plug negative numbers in, I believe. Let me see. Yeah, you should be able to plug negative numbers in. So the graph should go backwards here also. And the wind plot is having some issues graphing it. So when I'm in doubt, I'll bring up the Big Daddy. Sometimes we have to break out Mathematica instead and just write some quick code to do it. So let's plot x to the 4/5 times x minus 4 squared, and then I want my range to be x values between -10 and 10. Oops, 10. Ah, look at this. Even this is having trouble with it. All right. Never fear. Parametric plot instead. Well, I spoke too soon. There's our picture. It's not drawing the left side. It's having trouble with this to the 4/5. So here's what I'm going to do instead. I'm going to say x to the 4th, but then I'm going to raise that to the 1/5. It's not wanting to plug negative numbers in. That's the problem. There we go. Okay. I hope that that picture looks a little bit more believable. What do we have going on at 0? Guys, what do we have at 0? It's a cusp, though. Geometrically, it's a cusp, right? But the function's defined. Look, it goes back up. The function is well defined. So it's not that the function isn't there. It's that it's there and we have a cusp. So we actually have a local minimum here, don't we? We have a lowest point on the graph, which if you did not look at that x equals 0, you would not know that. And then where do we have the highest, like a local max happening? What value is that down here? Well, I bet you it's 8/7. I bet you it's 8/7. Let me go back to this one real quick. Let me see if I can trick this one into doing it. It was all about the order I did that. So if I go x raised to the 4th first, and then raise that to the 1/5. See, because when I raise it to the 4th first, if it was negative, it's okay with it, right? So it's not bothered by that at all. Times x minus 4 squared. It's weird the way these things behave. Tricked it. There. You can really see it here. Let me page down. You can see our cusp. You can see a local max happening at around 8/7, and you can see a local min happening where? At 4. So we identified those 3 interesting points on our graph. It looks like that would be the absolute minimum, yes. But see, when we talk about absolute minimum max, we need a closed interval. We need to actually close it off somewhere. I'm just getting us to see what we're doing is we're finding these points, and then later on in the exercises that follow, you say, okay, now cut it off somewhere. You know, lock the interval between, let's say, 0.5 and 5. Just look there. Now, if you look just there, where are you having your max and mins at? Where's your absolute max min? So our absolute minimum would happen here, and our absolute maximum would happen there, right? Does everyone agree? Absolute max would be here, absolute min would be here. But if I change this interval to 7, now do I have an absolute max over here anymore? I mean, absolute min down here. Absolute min's here, but this is not the absolute max anymore, right? Absolute max is, uh-oh. There it is. Okay. You see, but it's at an endpoint, which is why we always find the critical numbers. We plug them into the original function. We plug the endpoints into the original function. We compare the answers. All right, so did that address all the issues that you may have had with 31? The algebra involved there? We good? Okay. How about something like 35? Did you have any issues with 35? Yes? F of x equals x squared e to the negative 3x. I need the derivative, right? So derivative, I'm going to have product rule here. So that'll be 2x e to the negative 3x plus, now, what's the derivative of e to the negative 3x? Itself, right? The derivative of e to anything is itself. Times, the chain rule says, then go up here and take derivative of what's up there. What's up there? What's the derivative of what's up there? Negative 3, right? Because the derivative of negative 3x is negative 3. And then what else? Times x squared. I want some beef jerky. Real bad right now. That would be. The next step, I'm just cleaning this up. Right, just cleaning it up a little bit so that I can get a nice visual of what's happening here. Remember I said I don't like negative exponents? Right? I said that? Both of these are negative exponents, so I could drop that down and rewrite it as 2x over e to the 3x minus 3x squared over e to the 3x. But wait a minute, those have the same denominator, don't they? Right? So I can put those together and make it 2x minus 3x squared over e to the x, e to the 3x. Any issues with that? That's a pretty clean derivative. I'm happy with it. Now I'd like to know where it's 0 and where it's undefined, possibly. It could also turn out that it's never 0, okay, just so you know. I mean, you could get something where the derivative is never 0, which means you wouldn't have a critical number. So you'd just be looking at endpoints, possibly. All right, when's the derivative of this 0? Well, all I have to look at is what? The top, right? Just the top. Because I've already put it in that nice little fractional format. And this is a quadratic, but I have a GCF. I can pull an x out, right? 2 minus 3x. So what are your solutions here? 0 and what? 2/3. Now, let me also ask, when is the derivative undefined? Can I just put UND now? We've done this enough. When is it undefined? And again, this is a question, right? Don't know if it is ever undefined. So when you look at this derivative, the numerator is very well behaved. It's polynomial. It's a quadratic function. Those are well behaved. You have division here, so you do have to be concerned about that. But that means you have to figure out when this could possibly be 0, right? So you're saying, hey, wait, when is e to the 3x 0? Can't be, right? That can't happen. Remember, e to the x looks like this. E to the 3x also looks like this. A little bit steeper climb to it. So this is not going to have a solution. Now, there's another way you could do this. I don't know if you remember this, but whenever you have an equation, you can take the natural log on both sides. If you do, when you have an e, right, you can take natural log on both sides here. If you do natural log of e to the 3x should just plop out of this because they're inverses. So you get a 3x here, but then you go to your calculator or something, you go, what's natural log of 0? Undefined, which means this can't happen. So that would tell you also you have an issue. So this, there are no critical numbers from this part. So these are only 2 critical numbers. Okay, we good? Now all of your homework was just practicing taking derivatives and setting them equal to 0 and getting them undefined. Let's actually find some max and minimums on a closed interval now. So you will use that with some of the stuff we've learned, practiced already at home. I'm just going to pick kind of a, you want to start with the easy one, or you want medium, hard? What do you want? Medium? Okay. So how about this? I'm going to do number 46 in the book, which gives you a function f of t is t plus cosine 1/2 t, and then they want you to look on the interval pi over 4, 7 pi over 4. They want you to find the absolute max and min. Now, who asked me? Did you ask me about that global thing the other day, right? If you ever see the word instead of absolute global, max, min, they mean the same thing. Okay? Some books use global, some use absolute. They mean the exact same thing. So when you're asked to find the maximum and minimum values of a function, and you're given the function and you're given a closed interval, then we're going to use the closed interval method, which the first step is basically to make sure you're on a closed interval, but then you find the critical numbers. So let's go do exactly what we were doing a second ago. Find the critical numbers. Take the derivative, figure out where it's 0. So what's my derivative first? 1. Derivative cosine of something is negative sine of that something. And that something in there is actually a chain rule. So I have to take derivative of what's in there. So 1/2. Am I done with the derivative? You all happy with that? Yes? I can clean it up. 1 minus 1/2 sine 1/2 t. I'm pretty happy with that. I don't really think there's a whole lot more I want to do with it. Set it to 0. Okay, so y'all asked for group work. Let's do that. How about that? You wanted group work last time. Oh, let's all work in groups. It'll be fun. Okay, go ahead. Let's see if you can get those solutions. I'll give you like 3 minutes. See what you can do in 3 minutes. We can't take 20 minutes to solve a simple trigonometric equation. So let's see what you can do in 3.5 minutes. Everybody have the equation you're trying to work with? Because I'm about to take it off the board. Good? Okay. If you get something for the derivative being 0 and you feel good about it, move on. Make sure you check that the derivative, where the derivative is undefined also, if it's ever undefined. Are y'all stuck? We'll stay in groups. I'm going to give you all another problem to do here in a second. But what? So did you get sine of 1/2 t is 2? Did you get to that point? Trying to set this equal to 0. So just move that to the right side. Try and get rid of the 1/2. Multiply both sides by 2. And then say this has no solution. Why? Yeah, this is a sine curve, right? It's sine of the yellow. Sine of anything is bounded between -1 and 1, right? It's never going to be 2. This won't ever have a solution. So you don't have a place where the derivative is 0. And now you look at where the derivative is undefined. Does that happen? Well, here your derivative is up here, right? Sine functions are well defined. There's never any issues with them. So it's never undefined, which means we have no critical numbers, do we? We have no critical numbers. So where does the maximum have to occur then? At the endpoints. See, we know that the maximums have to occur either at the endpoints or somewhere inside. If it's somewhere inside, it has to happen at a critical number. We don't have any critical numbers, which means the maximum has to occur on the outside somewhere. So what I need to do now, that I've determined there are no critical numbers, I need to plug in to the function the critical numbers, which I don't have, and the endpoints. So I need the endpoints, what are they? Pi over 4 and 7 pi over 4. Where are these getting plugged in, by the way? The original function or the derivative? Original function. All right. So plug pi over 4 into the original function, and what do you get? Pi over 4 plus cosine of 1/2 times pi over 4. Yes? Which is pi over 4 plus, I'm out of room, cosine of pi over 8. So you get your calculator out and you figure out what that is as a decimal. And then do the same thing for the next one. 7 pi over 4 plus cosine, it should be 7 pi over 8. Does anybody have any questions, though, of what I've done? We're good? How did I? I moved this entire expression to the right-hand side, which made it positive. You could do that and then divide through by, or multiply through by -2 instead of +2. We should get the same result. You could do that too, but -1 divided by -1/2 is +2. Yeah. Well, the 2 wouldn't have messed with this. You can't divide it because it's trapped inside. Yep, can't pull that out. Anything that's trapped in the argument of the trig function cannot be pulled out, cannot be canceled. It's trapped. I mean, can't mess with it. One of those is bigger and one of them is smaller. So I'm going to verify with a visual. It was t plus cosine of 1/2 of t, right? Wasn't it? T plus cosine 1/2 t. But the interval was what? Pi over 4 to 7 pi over 4. Ah, shit. Pi over 4, 7 pi over 4. What should I have here when I do this? I mean, I'll have like the left point will either be the lowest or highest, right? The right point will be the lowest or highest. And in between, I should have no humps, no cusps, nothing. Let's see. Looks like a straight line, practically, right? So it looks like at the 7 pi over 4 is where I have the max, and at the pi over 4 is where I have the min. But you'd have to get like the decimal value if you wanted it to know for sure, like what the decimal answer was. So this one right here would be where we have our min, and then this right here would be our max. Go with me? Okay, I'm going to give you one now to work on in a group. I'm going to go back. Now I'm talking way back. Let's see. See how far back we can go. How about day? It's probably day 2. Where's the farmer? Remember the farmer with the pens? Yeah, I know. There was a bonus question on a test, right? Okay, so I'm just going to make up a new one. Y'all remember the idea? If you don't, then here it is. All right. Hey, a farmer wishes to build the pens shown below. How should he build them? Build them to minimize cost. So I need to show you a picture here, all right? Draw something for you. Here's the way it's going to work. This farmer is going to build a pen, and it will be like this. And let's make it 2 pens, identical pens, like that. Is that all right? And here's what I'm going to tell you. The total area of both pens must be 400 square feet. That has to be the total area of both pens. But here's where things get interesting. When the farmer builds the pens, this wall and this wall are going to be made out of like a metal fencing material, right? Some sort of metal fencing material. And this metal fence costs $30 per linear foot. We don't care how tall the fence is. We're just looking like from the top down on this, okay? Does that make sense? We're looking at the top down. So when I say $30 per foot, if this is a 10-foot wide fence from here to here, it's 10 times 30. That's $300 for that one section of fence. Make sense? And the other side down here is also metal. So that's going to also cost the same, $30 per foot. Now, this side part here and the middle part here and the middle part, or in the side part here, that's going to be a different material. It's got to be a little bit heavier because it's got to keep these animals from each other, and they want to attack it. I'm just making this shit up right now, okay? I mean, you know what I'm saying? Like it's going to cost something else, and so let's make it $52 per foot. Numbers where it's not easy to work out maybe what the best way to do this is. $52 per foot. Some good stuff. Some good fence. There you go. Understand the question. Everything that you need has been given. Now, I'm not going to ask you to work on this by yourself, okay? Not this first one. I'm going to help you get it set up, though. All right. We are trying to find how we should construct this, right, so that we get the minimum cost, right? This whole section is about maximum and minimum. So we want to find the minimum of a cost function. We need to come up with a function that represents the cost of building this, and then find its lowest point. With me? So the building of the cost function is going to be the challenge now. So tell me about the cost. Just if you're talking to me just like we're just sitting there, you know, just generally speaking to each other, what would you say? The cost, total cost would be what? Yeah, you would, but just, I mean, talk to me real just general right off the top. It's just going to be what? The cost is the metal fence cost plus the other fence. Oh, we didn't call the other fence. How should we distinguish it? That's metal. Let's say this one's made out of marble. Okay, it's marble. That's our marble fence. They're very, very high maintenance animals on this farm. Okay, so we got marble fencing and metal fencing. It makes no sense. So you're just trying to explain it to me. You're saying, all right, it's the cost of the metal fence plus the cost of the marble fence, right? That's how much it's going to cost me. So it's the cost of the metal plus the cost of the marble. See how I'm just subscripting those? So total cost is the cost of the metal fence plus the cost of the marble, right? We're sitting there drinking beer going, nah, how much is it going to cost? That's however much the metal fence plus the marble fence cost. That's how much it's going to be. I'm like, no shit. So how much is that? Well, how much is the metal fence? It's $30 per foot, right? But how many feet do you have? You don't know, right? So you better call it something. Call it X, right? So let's let this from here to here, that total distance be X, right? So how much would it cost for this side of the fence? X times 30, 30X, right? But then there's another one up there, 60X, right? Do y'all agree? So this cost of the metal fence is going to be 30 times X, but twice. So 230 times X's is 60X. Yes? So far, it's looking okay. Our total cost is 60X. Plus, now, how much is the marble cost going to be? It's going to be 52 times whatever this is, plus another one of them, right? Plus another one of them. And you want to call it Y, right? You want to call it Y? So if each of these is Y, and each one costs 52Y, and there's 3 of them, right? Then we said what? 156Y. Now there you go. So here's just farmer guy. How much is it going to cost? Well, it's the cost of the metal fence and the marble fence. That's how much it costs. And then you go and you say, okay, here's the algebra farmer. It says, well, that's 60X plus 156Y, right? And then you get the calculus person to come in here and say what? Calculus farmer says, well, now I'm going to tell you what X and Y should be so that your cost is the smallest it can be, right? Because I can build this fence a lot of different ways, but I want it to be a certain way, right? Yes? Y'all following me? All right. So now let me try and get our heads around this. This is a cost. It is not a function of X. It's a function of X and Y. We have 2 variables, don't we? We need to get this in terms of one variable only so that we can talk about the graph of it, right? Like f of x. Sorry, this is a different class. That happens to be a function of x and y up there, so I don't want you looking at that thinking something else. All right, so this, what information have I not used? The area, right? The area of this thing has to be 400. So I'm going to do a little side note over here because I'm trying to keep this all on one page. The area must be 400 square feet. What is the area of this thing? What, by the way we drew it, careful, area is length times width, isn't it? It's just x times just y, right? The area of a rectangle, the whole thing, the area of this whole enclosure has to be 400 square feet. So this x times that y should be 400. So I'm going to write that down over here. X times y must be 400. Total. We'll say total. Change that up there to total area. So what is the value of knowing this? If you know this, right, then you can come back over here. See, you have x and y in this equation. You want, I said, all x's, right? Or all y's. It doesn't matter. You just want one variable instead of two. So, but this over here gives you a relationship between x and y. So solve one of those. Solve this equation right here for either x or y. It's up to you. X is 400 over y. That means I can come back to this equation right here, and I can replace x with what? 400 over y. So my cost now is 60 times 400 over y plus 156 y. Everyone see that? And I'm going to go to my next page, and I'm going to just multiply 60 times 400. That's what? 24,000 over y? So watch the way this is going to look now. My cost is 24,000 over y plus 150, what was it, 6y? 156y. And notice the way I wrote my cost. I wrote C of y. That's to stress to you now that we have basically gotten our cost down to a function of one thing. Instead of you having to tell me, one side of the pen and the other side, just give me the y. Just tell me how long the marble fence is going to be, and I will be able to tell you everything about the cost. You with that? Understand that? And now I need to figure out, am I on a closed interval? Is this function restricted to a closed interval or not? This is a key to the problem right now, because if it is, I can use a closed interval method. So take a look at this. Take a look at this fence for a second. Give me some restriction on y. What can y not be less than? This right here. Give me a smallest value of y that makes sense. 1.1. How about 0? I mean, like, it wouldn't even make sense to have 0 here, would it? We wouldn't. I mean, you have no animals in there, right? But would you agree that 0 would be like a lowest point for us? Right? A lowest point? Okay, so we're trying to throw a restriction on this. I can say that y has to be, 0 can be the smallest, right? Do you see a problem with this, though, already? At 0, we're undefined. You cannot define this on a closed interval, can you? You see the issue I'm running into here? We'll address that in a second. Is there a biggest value that y could be? 400? If y is 400 right here, then what would x have to be? 1, right? Okay, so what if y was 800? Then x would have to be a half. That's possible, right? What if y was, I don't know, 1,000? 4,000 would be 110, something like that. I mean, no matter what this length is, I can multiply by something and get 400. What am I getting at here? I really hope I'm trying to, like, I'm painting this picture pretty clear for you. We have a function of one variable, don't we? But what don't we have? We don't have a closed interval. Do you see that? Like, I can't say 0. Why can't I say 0? Look at my function. It is undefined at 0. So you can't tell me to look at 0. You can tell me to look above 0, so make it an open interval instead, right? How about stopping it? You said I could stop at 400, but I said, yes, I could stop at 800. And then you could go to 4,000 and still work. In fact, I could make this thing 1,000,000,000 feet long and make the width of it infinitesimally small. Now, it would make no sense to do that. But purely from the sake of the math of it, there is no restriction on my function, right? There is no restriction. Yes? This is a key point because we have two ways of getting maxes and minimums of functions. We have a closed interval method, and we have an open interval method, which we haven't even talked about. This is an open interval because you can't close it. So algebraically, we are stuck right here. Right? Algebraically, we're stuck. We can't do this problem with the closed interval method. But we're going to finish it with closed interval method because we can make it make sense. I mean, this is a freaking pen for an animal, right? If we know the animal is, let's say, a pig, we know that we are not going to put a pig in a fence that's only 1 foot wide, right? So why don't we just make 1 our lower bound? Is that okay? Do you understand? I'm circumventing the problem of this being an open interval by introducing the actual living situation, right? If someone just gave you this function out of the blue, it was in your book, and they said, you know, give me an interval, closed interval domain, you wouldn't be able to close it off. But in the context of the real physical world problem, we can. So I'm going to, because this is, let's say, a pig, I know that the lowest I have to look is 1 foot for y. And then what, 400? I mean, you've got only so much space, right? You've got this farm. You're not going to make a pen that's 800 feet wide and then a half a foot. It's just not going to work. So 400 is a good top for you, right? We know definitely that that should work, right? Somewhere in there, we can find the max and min. So what do we need to do now? If we have that function on a closed interval, we need to take the derivative. Now I'm going to rewrite the problem. I'm bringing that over y to the top. Now, you work in groups to see if you can find me the critical numbers of this. Find me the critical numbers, and then try and tell me where the minimum occurs. Okay? The grade is online. It's not on. I didn't put the grade on here. I do in the morning. I've got something going on though, so it would be in the afternoon, like 1 till about 3 or 4. If it's gonna be after 3 though, call me or text me. I get a notified for that. So you have a pretty big 2 to 3. Yeah. Okay. You don't get it yet? You probably need a calculator. What's that? If you think you've got it, let me know. I'll come by and take a look. Pardon? You have a critical number? Okay. You're going to need to test. Yeah. Yeah, you're treating y like x. Okay. Remember earlier I said let's solve. It was x, y equals 400. So let's solve for x or y. So we'll pick y. They would have picked x probably. Well, no, they picked x, and then it would have been the other way. It would have been a little less confusing. Oh yeah, yeah. Okay. That's habit. I only do that because it's habit. This is the way I did it. Taking the derivative of this, the negative 1 pops out, and then you subtract 1, it becomes y to negative 2. The derivative of 156y is just 156. And then I rewrite this. I drop the y squared to the bottom. I do get a common denominator. That's just the force of habit. And once I do that, that's my derivative. And then I set it to 0, which means I just set the top to 0. And that's just a quadratic equation. I just move things around, eventually take the square root on both sides. So I get a value of y is 12.4. And now what I need to do is I need to plug that in to the original function and plug in the endpoints. So I want C, I want to plug in the endpoints and that point. I'm going to go to a new page. I want C of 1, C of 12.4, and then what was the other endpoint? 400. And I will plug those in to the original function, which was 2,400, or 24,000, right? Over y plus 150, what was it? Is this right? 156 times y, which was 1 here. So I'm just going to the original cost function and replacing my y's with 1s. And then I'm replacing my y's with 12.4. And then I'm replacing my y's with 400. Did anybody do that yet? Okay, what did you get for 1? Okay. For 12.4? 869.88, close enough. And what about for 400? I think it's probably pretty obvious what your minimum is there. So if you have to build a fence with those restrictions, within the reasonable expectation that you've got to have at least 1 foot wide, and that you're never going to exceed 400 feet as a width of this pen, then it's very reasonable. Then the optimum solution, the best way to build this pen would be to make your y value 12.4. We have not answered the question, though. Look at the original question. How should she build the pen? So I want to know what the dimensions of this pen should be. I mean, all you've told me is how much it's going to cost me. I want to know how to build it. I need the y to be what here? 12.4, which means I need to figure out what x is going to be. But you can get x by this equation right here. Take 400 and divide it by 12.4, and what do you get? What is it? 32.26. So I'm going to put here, in summary, so y equals 12.4 implies that your x would be 32.26. Of course, these are in feet. And you don't even have to compute this. The minimum cost would be what? About $3,869 and change, whatever. Close enough. Expensive pig. Okay. You get the idea, though, right? I mean, well, I'm saying I'm answering for you. Do you get the idea? You have a geometric situation. It's not as simple as, okay, add these sides up, get something. The cost is going to come into play here, right? Your cost. Yes. Uh-huh. Divided by y? All we were trying to do was get this cost function right here to have one variable instead of two. So instead of having x and y, I needed to just have x's or just have y's, right? Because right now, in order to find out the cost, I need to know both the x and the y. In the next line, I only need to know one thing. So this is a function, like the true classic function. You have a variable, right? Something you plug in, something that comes out. So I can graph it. so I can find max and mins. Can't do it here. I don't know if I'm answering your question. I asked the class, I said, I can use this restriction, which we call constraint, to figure out the relationship between x and y here. I can solve this equation for either x or y. I asked, what would you like to solve for? I was told, solve for x. You could have solved for y. If you would have solved for y, you would have got x. Y is 400 over x. You would have replaced this with 400 over x, and this would have been 60x plus whatever 400 times 156 over x is, and you would have got the same answer. Well, not same answer. Your answer at the very end of that would have been 32 point whatever we had for x. Then substitute back in, would have got the 12.4 for y. That make sense? Good question. Good question. So let me do one more of these. We only have 20 minutes, but I'll help set it up. I'm having you do word problems. Your homework is not going to be word problems. Your homework is just going to be finding the max and min on closed intervals and just practicing the derivatives and plugging in endpoints. So more practice. But I'm trying to get you to see where we're going with this, all right? So how about this? We'll do something geometric again. We'll do something that has cost in it again. Let's say that I have a river. And it's a very, very straight river, okay? And let's say on one side of the river I have a building, and I'll call that building A. And on the other side of the building I have another building, which is building B. And it's downriver. But directly across, go downriver. Let's say if I go directly across to a point and I measure the distance from that downstream to B, let's just say that that's 3,250 feet. It's a very straight river to be, over half a mile long, straight as an arrow, okay? Yep. Yeah, that's right. Well, it's hard to find a river in Texas to begin with. All right. So this is a company, right? I have two buildings. One is across the river from the other. And what I'd like to do is I'd like to connect these buildings that I just built. I'd like to run fiber optic cable to connect the buildings, all right? So we can communicate high-speed stuff, right? So we're going to lay some fiber optic cable. So what we're going to have to do is kind of decide how it's going to work. We could go directly from point A, or from building A to building B, right? Straight line, and we could run the fiber optic cable that way. That would be the shortest distance, wouldn't it? Straight across. However, I haven't thrown this in here. If I'm going to run the fiber optic cable across the river, I have to pay a company to bury it underwater, which requires very special care to prep and dig under the river and have special conduit that's completely waterproof, all this stuff, right? Certain cost for that. Going above ground is completely not going to happen. Okay, we don't want it to be tampered with. We don't want people to be able to assess it from the outside. We want this buried, all right? So we're going to bury this cable. We got to go underwater to do it. And we could go straight across the river. That would be the shortest distance underwater, right? Yes? And then the rest we have to bury it underground. So the company that's going to bury this for us costs a certain amount to bury it underwater, a certain amount to bury it underground. It's much cheaper to do it underground because they just get a trencher and they just dig it out, and some guy just sits there, right? But underwater, it's a much more complicated process, right? So I need to give you some costs, and I'm going to be making these up, so I don't know how this is going to work out. I'm going to tell you right now that the cost to go underwater is throw me something. $100 a foot? All right, well, I said throw me something. I'll take it. $100 a foot. Oh, I didn't tell you how wide the river is. We would know that, though, right? 120 feet. We're definitely not in Texas. So they're going to charge us $100 a foot to lay that thing underground. And how much above ground? Cost above. Wait, no, not above ground. Underwater is at, okay, under land, all right? That kind of doesn't make sense, but you understand what I mean, right? It is under the land, right? It is under the land. We'll make it cheaper, but we won't make it so cheap that it's like a no-brainer. You know, if it was like a cent per foot, then it would be pretty obvious that we just need to go straight across the river and just get over as fast as we can, right? Shortest distance, and just let the rest be land, right? Yeah, so here, let's just make it something where it wouldn't be that obvious. How about $65? And again, I don't know how this is going to work out. So let's look at some options as to what we could do, all right? Just a couple of options. I could go, like we said, straight A to B. That would be the shortest distance, but it would all be underwater, wouldn't it? I could go straight across and then straight across like that. That would be the shortest distance underwater, but the longest distance on the ground, right? Under the land, or digging a trench on ground. So maybe there's some place in between where I cut across at a certain angle, right? And then come across the rest of the way on the land. Maybe there is. Maybe there's some optimal, cheapest way of doing it where instead of going straight across and over, I go through at an angle. Yes, I'm going to incur more cost doing this than I would straight across, but maybe that's the way I want to do it. Do y'all understand? It might. And the only way we know is by running the calculus on it. That's the only way we're going to know. So you wouldn't want a guy to be out there going, well, that's the shortest distance. Let's just do that. You know what I'm saying? Okay, so let's try and come up with a cost function for this. So what's the cost? Well, it's the cost underwater plus the cost under the land, right? So what is the cost underwater? It's $100 a foot, but how many feet are we going to go across the water? We need to actually draw some, let's label some stuff here, right? We need to draw some stuff. Okay, so I'm gonna take some stuff out of here just so we don't confuse our vision here. I'm guessing right now that this distance from here across the river, I'm going to have to go across the river, right, at some point? And that distance could be straight, it could be directly connecting, right? So why don't I call that distance y? Just call this y. Once I travel across y, a certain distance, I will then have to travel the rest of the distance on the ground, right? And I should call that maybe x. Do y'all agree with that? Now, it might turn out that x is going to be 3250. It might turn out that x will be 3250, right? In that case that x was 3250, y would be what? 120, because you'd be going straight across. Now, what happens in the event that x is 0? Then you're going to go straight across, right? Do you see, though, by doing this, do you see that I'm actually creating something where I'm going to have a closed interval? Because x is going to be, what? The smallest could be 0, but the biggest is what? Whatever the heck that is, 3250. You see, I have a closed interval. I have a restriction on x that's closed. I just need to come up with a function that gives me the cost based on x. All right, so let's keep going. So would you agree that the cost to go underwater will be $100 times the y? Because y is the distance we go underwater. So this will be, cost is 100 times y. plus, now the cost to go on the land is what? 65 times x. And why can I not just come in here and say, oh, take the derivative and be happy? You have two variables, right? Your cost depends on two variables. Now, believe it or not, in Calculus 3, you can do this problem without any problems because we can handle functions of two variables in Cal 3. But in here, you have to get everything in terms of one variable before you can mess with this. So we need to get either the y to be something in terms of x, or we need to have the x in terms of y, and it's our choice. I liked, again, trying to get the y out of here, get x's in here, because I already know kind of the restriction on x. Y'all follow that? So what have I not used in the problem? I've used the cost here, and I haven't used this, have I? Like in my formula, I haven't used that. And I haven't used the 120, so they've got to come into play somewhere, right? Remember, the goal is to get y in terms of x. Y in terms of x. So let's start looking around here. Y, I think I heard someone say hypotenuse. Y'all agree that y is a hypotenuse? I'm going to draw this on another page. We said from here to here was x, right? We know that this is y. We know one side of this right triangle, don't we? It's 120 right here. And if I just knew one more side here, I'd have a Pythagorean identity relationship, right? A squared plus b squared is c squared. The whole distance here is 3250. So this distance is 3250 take away x, isn't it? And that's the key right there, seeing that relationship. Because now you can create the relationship between x and y. By the Pythagorean identity, I know that 3250 minus x squared plus 120 squared must be y squared. Agreed? These numbers are going to get big, but that's all right. I can get y by taking the square root on both sides, can't I? But let's just actually multiply this out. So I'm going to have to FOIL this. The numbers are going to get nasty, all right? 3250 squared, oh my goodness. All right, this is going to be 105,62500 minus 3250 times 2, so 6500x, and then plus x squared, and then plus 120 squared, right? 14,400 must equal y squared. So I expanded this out, which gave me 3 terms, right, when you do an expansion like that. I squared that, got this, and then now let me collect some things together. Let me take this number and let me add that. And I'll put this in descending order. I have x squared minus 6,500 x plus 105,76900 equals y squared. Have I lost anybody? Are we all right? Now remember, I'm trying to get y in terms of x, so let me get y by itself over here, which means I'm going to square root both sides. So I'll go ahead and just do that, and I'll turn that into y. And now that means I can go back to my cost equation, and wherever I see y, I can replace it with this. It's not pretty, but that's what it can be replaced with, right? So here, rewrite the cost function. The cost was equal to the cost underwater, which was 100 times y, wasn't it? So that's 100 times this. 100 times that square root of x squared minus 6500x plus 105,769,000. So that's 100x. I mean, sorry, 100 times y plus 65x. That's our cost function. Do you see this problem is a little more real world than like a farmer building a pen for two? I mean, it's a little more applicable, right? And it just goes to show you that the numbers in the real world are never going to be nice. Like, it's never going to be pretty numbers. It's always going to be something harder. So we have to be pretty comfortable with the easy number stuff to get our heads around this. All right, do I have a function of one variable here? Yes. Is it defined on a closed interval? Do you have a restriction on x for me? 0 to what? 3250, right? So now I can use the closed interval method. That means I need to take a derivative of this, which may look bad, right? It may look bad initially, but let's see what happens. And I only have like 5 or 6 more minutes to do this. Whoa. All right, so my derivative is, now the 100's going to stay, right? 100's going to stay. What's the derivative of the square root of something? 1 over 2 times the square root of what's there, right? Well, won't that 2 that's on the bottom make that a 50 on the 100 that was out there? I'm trying to do this as clean as possible. 50 is still there. On the bottom, I have the root still, right? The root of what's there. But what do I still have to do? Times the derivative of what's inside. And that 50 will be multiplied times it. So I'm going to put that derivative of what's inside here. What's derivative of what's inside? Good. That wasn't so bad, right? That part? Okay, then what's over here? Plus 65. Hey, that wasn't so bad for a derivative. Right, I think. Now, I'm going to have to set that to 0. And I've been getting common denominator, but you see how bad that's going to be when I put that fraction up here? Yeah. I mean, but I could do it, yes? Okay. Let's try and clean this up. Yeah, I'm really debating which way I want to go with this. How about I do this? Let me set this equal to 0 now. And just tell me if you believe that this would be true. I'll multiply that 50 through. So 100x minus 6,500 times 50. Just punch it in real quick for me. Negative. So 325,000 negative. All I did was distribute it there, right? Over my square root of all that crap there, right? I'm not going to rewrite it because I'm almost out of time. But you all understand all that crap's still under there, right? And then plus 65 equals 0. So would you mind if I just take that 65 to the other side and make it negative 65? Is that all right? That was supposed to be plus 65 equals 0, so I moved that 65 over. Now I'm going to multiply both sides of the equation by the root stuff. When I do that, the roots on the left cancel, which leaves me with the 100x minus 325,000 equals negative 65 root of all that stuff. Are y'all still there? Okay. Now, This is what we would call a radical equation. Have a square root in it, right? So anytime we have a radical equation, we always like to square both sides. That's what we do. But I'm going to divide through by negative 65 first. Divide it here and here. I'm going to be getting decimals, so y'all just hang tight. I'm getting negative 1.5. I'm going to round two decimal places. 14x. I'm taking 325000 dividing by 65. Ooh, that goes in nice. So I get plus 5,000 equals the square root of all that junk. Okay, just divide it through by negative 65. Now, square both sides of the equation. When I square the right side, I get just what was underneath it, right? Which was x squared minus 6,500, right? X. And then there was a big number. What was it? 10576,900. That's what was underneath the root, right? On the right side. Have I blown the doors off, or are y'all still here, or what? You're still all right? On the left side, I have to square the left side, don't I? Which means I have to FOIL this, right, with itself. I can't just square each one. I have to FOIL it, which I'm going to do. You should get 2.37x squared. Then you should have, well, that came out kind of nice. I'm getting 15,400x, and then you have to square 5,000, which kind of sucks, because that's 250, and then 5 zeros. 1, 2, 3, 4, 5. Ugly as this might look, what is it? It's a quadratic equation, isn't it? I square both sides there. This is a quadratic. So move everything to one side. I'll subtract x, so this will become a 1.37 x squared. I'll subtract, no, I'll have to add 6,500 to this. So take your 15,400, what's that? That's all right. So I'm getting a negative 8,900 x. Then I take this ridiculously big number and subtract this ridiculously big number. 250, 1, 2, 3, 4, 5. Subtract 105,769,00. I'm still getting a big number. It's 14423,100 equals 0. God, I hope this works out right because I've been working pretty fast through this. And I'm out of time. But what can you use to solve this? Quadratic formula, right? X should be equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Yes? Okay, and you get an answer. I'm just going to have this solve it real quick. Do you all mind hanging out for a second or not? I just want to see if our solution is even close. Because we want it to be between 0 and 3250, right? So I have solve. Can't see it. There it is. 1.37x squared minus 8,900x plus 14423,100 equals 0. If all the math all the little subtleties were done correctly, I'm getting 2 solutions, which I should get for a quadratic, right? Do they live in our interval? One of them does, right? One of them does. The other one does not. So that means I would want my x to be 3,097 feet. And that would give me the least cost. Now, I still have to show it's the least because I would have to compare plugging in at the endpoints, right? Plug it in at the endpoints, and I'd be able to tell. Do y'all follow this or not? Okay. All right. So your homework is nothing like this, but we will be doing problems like this in the next few sections. Your homework is just more practice with finding these critical numbers and plugging in at the endpoints. So go ahead and go back to page 209. And I had you go through what, 35? Go ahead and go through 37 through 49 odd. You did 37, 39? Okay, so you can just go the rest of the way. And then if you want, to have continued practice with that, you can try those evens in there also. The more practice you get, the more used to the algebra you're going to get. And then when we get to the problems later, you won't just be like, what the hell is going on here, Sorry to keep you so long. You'll have a good day.